Okay, so I'm very happy to talk about the 2020 Nobel Prize in Physics, especially about Sir Roger Penrose's contribution and his honor as a result of his contribution about gravitational collapse and the inevitability of space-time singularities. So this is a rough outline of my talk. First, I'm going to talk about an introduction to black holes. How do we know they exist? And of course, everybody knows last year we had the first image of a black hole courtesy the Event Horizon Telescope collaboration. They released an image of a telescope of a black hole, which has become very popular. However, that is only the final nail in the coffin. We have known about black holes. We have a lot of evidence of them from various different sources across various different mass ranges from other observations as well. So I'm going to talk about the kind of black holes, for example, supermassive black holes, which we know reside at the center of galaxies. I'm going to talk about the evidence about them. Then I'm going to talk about a different kind of supermassive black hole, which are far more active. They're known as quasars. They are highly active black holes with huge accretion disks. They're most luminous objects in the sky. And then I'm going to talk about smaller or solar mass black holes. For example, we know a significant fraction of what we call gamma ray bursts lead to the formation of black holes. I'm going to review that evidence. And I'll also talk about other ways which we spot or locate black holes in the sky, which is looking at X-ray emissions from accretion disks, which are formed when a black hole cannibalizes a companion star. The enormous tidal forces of the black hole rips the star apart and starts consuming the guts. And as a result, an accretion disk form, and that accretion disk emits a lot of X-rays, and from that we can detect indirectly, we can detect a black hole, existence of black holes. Okay, after that, after reviewing the evidence, I'm going to talk about some of the mathematical properties of black holes, for example, horizon, singularity, and then some extreme physical effects which we expect to encounter when we are close to the black hole horizon, for example, extreme time dilation, gravitational time dilation, spaghettification due to enormous amount of tidal forces, especially for small black holes, which people worried about at the early years of black hole research. And then, since this is a talk which is dedicated to Roger Penrose, um, I will talk about a process of energy extraction from rotating black holes, which was first sort of brought to attention by Sir Roger Penrose. So I'm going to talk about this Penrose process by which one can mine the energy of a black hole. Actually, and it will turn out this is much more efficient than extracting energy from stars and maybe future civilizations who are capable of interstellar travel would colonize these kind of rotating black holes and live off the energy, support their civilization off the energy obtained by extracting energy from the black hole, rotating black holes using the Penrose process. However, instead, these are all mathematical nice properties. I will also discuss how, through various other simulations and other theoretical calculations, we came to the conclusion that implosion is compulsory and collapse of high mass stars, masses more than 2 to 3 solar masses, inevitably would form black holes. And these are not some mathematical artifacts or some unphysical solutions. They are, in fact, very common, inevitable solutions of Einstein field equations. I'm going to talk a little bit about the history, how we came to believe that indeed this is the implosion of this high mass stars is compulsory to form black holes. They will sink below the horizon, and the collapsing matter would get crunched out of existence, according to Wheeler. Then I'm going to talk about how people started to think about singularity theorems. This implosion and compulsory, although there was a lot of sort of supporting evidence, people still had difficulty swallowing this idea because they believe maybe the calculation using some kind of oversimplified assumptions, which is kind of guaranteeing this result. Maybe if we take more general initial conditions, this kind of black holes won't form. There would be no horizon, no singularity, nothing. So people started to think about singularity theorems much before Penrose, and I'm going to talk about Wright-Choudhury's equation and Wright-Choudhury's contribution, who was the first person to really work out singularity theorem. And in particular, what he actually showed is something which is known as the focusing effect. That is the the phenomena that we have focusing of geodesics. One can think of it, null geodesics. But this focusing effect doesn't really always, in general, lead to a singularity. In fact, it leads to the formation of a caustic, and light rays or time-like rays can diverge after focusing through a caustic. So this is not really a singularity. Although in his case, the equation, the kind of solution he wrote down it's one of the cases in which you do have a singularity formation. But generically, this focusing effect doesn't lead to singularities. Instead, it leads to formation of caustics. Of course, then I'm going to talk about, I'm going to give a brief sort of overview of some of the global tools which Penrose, with a unique mathematical background, brought into general relativity, which has enormously benefited the field and completely changed the way we think about general relativity. For example, I'll talk about Penrose's conformal diagrams, which allow us to see what happens at the edges of spacetime and the various kind of infinities he thought of. And then I'm going to talk about causality and horizon, how Penrose's ideas give us some kind of global idea of what these are. And then finally, I'm going to talk about the singularity theorem of Penrose and the important concept which was missing in Wright-Choudhury's the earlier attempts of singularity theorem. And Penrose was able to identify the missing ingredient, which is a trapped surface. Once you have a trapped surface, the focusing effect combined with the trapped surface inevitably leads to the formation of a singularity. So I'm going to talk a little bit about what the assumptions of this theorem are properly. But as I said, in a nutshell, this focusing effect plus the assumption that there is a trapped surface is enough to guarantee a singularity will form. In a nutshell, that is the basic idea. I'm going to talk about what a trapped surface is. I'm going to show a picture of a black hole and explain how the things inside the black hole, you have trapped surfaces. And finally, I'll give a conclusion and outlook. The outlook will be positive because we have a lot of gravitational experiments coming up in the next few decades, and we will learn more about black holes and singularities and other stuff, other important, interesting phenomena, which so far was just theoretical equations. And now we will be able to verify those and see those startling physics, sometimes almost like science fiction. Those kind of effects we will be able to see in the near future. Okay, with that, let me just begin. This is the famous image of a black hole, which most of you are familiar with, which was released last year by the Event Horizon Telescope collaboration, which shows the black hole in the galaxy M87. As you can see, there is a dark region in the middle, which is supposed to be the black hole surrounded by light rays. So this is, of course, as I said, this is not the conclusive evidence of black holes. This is the final nail in the coffin, but we've known about the existence of black holes for a while now. There exists a lot of other independent data which indirectly point out to the existence of black holes. So let me just go to the next slide where I review all these other evidences for the existence of black holes. So here, what we have here is one of my favorite videos. This is video is prepared by the European Southern Observatory around 2002. And what we are looking at is the center of the Milky Way galaxy, our host galaxy. This cross is the location of a supermassive black hole, which is at the center of our Milky Way galaxy, known as Sagittarius A star. Most of you know this. So let me play the video. So what we see here is the motion of a bunch of stars around that supermassive dark object at the center, at the location of the cross. And let's zoom out a bit and let's follow the trajectory of the stars. In particular, we'll look at this star. Let's see. As you can see, the star is being whipped around at enormous velocity around the. Let's look at this once more. 1 second. Yeah, okay. As you can see, these stars at the center of our galaxy are being whipped around the central dark object at very high speeds. If we zoom out and we follow in particular, the trajectory of this star, you'll see it is going to be. So this object is our host galaxy's central supermassive black hole, and the star which is being whipped around is whipped around at the speed of the star, which is being whipped around very fast. It'll turn out to be almost 2% the speed of light. So you can imagine when a star is whipped around at 2% the speed of light, you can compute the central mass, which is actually causing this kind of enormous gravitational centripetal pull, which is able to whip around such a huge mass of star at such high velocity. And it turns out this is the famous figure, which is 4 million solar masses. So we have an object which is 4 million solar masses big, lurking at the center. And you can see from the dimensions, this is 10 light days. Very short. The second half of the prize was given to Reinhard Genzel and Andrea Goetz for conclusively establishing this. So we have known this for a while now. So I think this picture was developed in the 90s, but then it was published in early years of the millennium. So it is pretty conclusive evidence. I like this video very much. It just gives you a very nice demonstration. One thing about this video is that if you look around the stars, around this black hole which I talked about, nothing really crazy is happening. Of course, they're orbiting, but other than this orbiting, everything looks stable. Everything is on a stable orbit and everything. So our galaxy, the central black hole at the center of our galaxy, is not really a very active, violent black hole. It's a very quiet kind of a black hole. Everything is stable around it. However, things were not when we look back at the early universe. So again, this is video of it's an animation which is made by the European Southern Laboratory once again. And this is about something which we see in the sky, which are known as quasars. So let's just play the video so that you can see. What's happening here is that in the early universe, when galaxies were forming, they were full of a lot of hot young stars with supernovae quite early. Now, usually supernovas form neutron stars, they're not black holes, but then these stars, supernova, which were close by, they kind of coalesce to form black holes at the center. And this kind of, in young universes, this is very common. So these kind of objects, quasars, are sometimes known as active galactic nuclei. So we can see these, we observe these, it's been observing this for a while now, so I think mid-60s or mid-50s. And we see these quasar objects, which are known as quasi-stellar objects, at about very high redshifts, at redshift of 7, which means we are looking at maybe 7 redshift means almost 13 billion years back, and the universe is what 14 billion years back. So we are looking at the galaxies which were within 10% of formation of the universe after the Big Bang. We are looking back in time that much, and we see a uniform distribution of these objects in the sky. The first one, of course, was detected by Martin Schmidt back in the 1950s. Now we see a uniform distribution of these in the sky. In fact, you can, if you have a decent enough telescope, you can see one in your backyard. If you go in your backyard, if you know where to look at, this is the quasar 3C273. People who are science fiction enthusiasts already are familiar with this quasar. It appears in a lot of sci-fi stories. And as you can see, it is I said it's very far away, high redshift of 7, yet it outshines all the other galaxies in the background. You see, such a very bright object. And the reason is that, these quasars, central black hole, it's actually devouring about 100 to 1,000 stars every year. That amount of matter, it's falling into the black hole, and then there are gigantic magnetic fields which are causing these kind of accelerated emission of particles, not unlike the LHC the particle accelerator which we have, 1,000 light years long, these particle jets which are coming out, just like an accelerator-like effect. So, and we know about these objects for a while now. So these are also supermassive black holes. The difference between what I showed earlier is that these are very active, violent black holes which are emitting a lot of light or a lot of radiation and matter. Now, if we come down a scale, we also see black holes in the solar mass range. Some of these are known by the phenomena which we observe as gamma ray burst. Let me play this video of a gamma ray burst. Again, we have known this about these for a while now. Actually, it was known by the US military long before physicists knew about this. They were detected by US spy satellites which were put out during the Cold War to monitor the weapons program of the Soviet Union. And instead of, they would see these flashes of gamma rays coming from the sky and not from, it took them towards the ground, but from the behind them. So we see one gamma ray burst almost a day at a very high frequency, almost a day, and these bursts last for around 30 seconds, something like that. And so why do we think these are black holes? Well, the reason is that what I showed in the video, you must have noticed that these are like a bit scaled down version of the quasar picture which I had. Again, we had jets going out of this. So these are scaled down version of this quasars. What we have is a solar mass object or maybe few solar masses. Actually, what we're looking at is a supernova explosion. However, these are not the average kind of supernova explosions which I'm talking about. These are actually bigger or higher masses, which are sometimes known as hypernova. And we believe a significant fraction of these hypernovas are leading to the formation of black holes because of the beginning mass, which is much larger than one solar mass, maybe of the order of 10 solar masses or more than that. Then the inevitable conclusion of that must be a black hole. There is no way you can form a neutron star at that kind of mass. And these must be, significant fraction of this must be black holes. So we have ample evidence of gamma ray bursts which have solar mass kind of range black holes with quasars which are very active, million solar mass or billion solar mass black holes. And we also know that centers of our own galaxies have black holes. Another evidence for black holes comes from looking at accretion disks. Accretion disks are, most of you know what these are, but let me play the video. You have a black hole at the center, and there is a companion star, but this black hole is going to suck and rip out the star and slowly swallow the guts of the star in this kind of a spiral where matter is then falling into the star. Let me just play the animation. Again, this is from NASA. NASA has very beautiful educational videos as far as astrophysics is concerned. So by accretion disks, we can actually locate or we can spot more black holes in the sky. What happens is that these gas atoms, which are actually the entrails of another nearby star, which has been ripped apart by this black hole, the enormous tidal forces of this black hole. Now, when these gas atoms fall into the black hole, they collide with each other, and this friction between various gas atoms cause the temperature of these gas atoms to this accreting matter to go up to several million degrees, whereby it starts emitting X-rays. Now, from these X-rays emission, from the Doppler shifting on the the spectrum of these, measuring the redshift of these light, we can figure out what velocity of this accretion disk is, and by that we can indirectly conclude what is the mass of this object here. And from the distance or location of the horizon and this mass of this object, we can conclude that indeed there's a lot of mass here which is confined in a very compact place. It cannot be anything other than a black hole. So this video animation is a bit lengthy. It actually shows several facets. If you have time, you can go and look at this in your spare time. And what kind of effects you can look at these accretion disks. It's a full simulation of an accretion disk. So all I'll mention about is this light ring you see. It is not the horizon. Horizon is somewhere deep inside. This is the last stable photon. This is the last stable photon orbit, which is actually 3/2 the size of the horizon. So it's a bit outside, 3/2, 1.5 times larger than the horizon. The horizon is somewhere pitch black inside. So here you can see some of the light trajectories which is being deflected and getting into the detector. Various processes which happen in the accretion disk. I'm not going to go through this video entirely, but let me just, these are X-rays. So this is how we detected the first ever black hole in the sky using an X-ray detector. Let me just go to the next page, which is Cygnus X1. Right, Cygnus X1 is the first X-ray source which we suspected to be a black hole, and it was back in the 60s, I think, when we came to know about this. So it's located in the constellation Cygnus. That's why Cygnus, and X is for X-ray. It emits X-rays. It was initially called XR1, but now we call it just X1 because X already includes X-rays. So from whatever evidence I've presented, so it must be clear to you now that there is a huge mountain of evidence of black holes in the universe. We have quasars and supermassive black holes at the center of galaxies. We have stellar mass or tens of stellar mass black holes, which we see in gamma ray bursts. And from the various accretion disk phenomena we observe in the universe, we conclude there must be other black holes as well. So there is an ample body of evidence. As I said, last year's picture was the final nail in the coffin. Now we have even a nice picture of it. But even if we didn't have that, we were pretty sure that black holes are out there, and many of them. Okay, so this was all the experimental evidence. Probably my colleague, Professor Shantanu Desai, in his talk will further give you details how actually these imaging takes place. I'm not an expert in that. He will be able to tell you how these videos were actually obtained of this Milky Way galaxy, the center of the Milky Way galaxy. It's an incredible achievement to film such a thing. And then I'm now going to move to some mathematical properties of black holes, or how we mathematically see them. So from here on, you'll see more equations and fewer and fewer pictures, maybe. So black holes, they were originally posited as dark stars in the 18th century, late 1790s, I think, by Mitchell, this British philosopher Mitchell, and the French physicist Laplace, or mathematician Laplace. Both of them independently, almost simultaneously, arrived at this kind of a conclusion. They knew about Newton's theory, so they knew about the concept of an escape velocity, the velocity at which you need to fling a projectile so that it escapes the gravitational attraction of that planet. Most of you have learned this in middle school or something. And you balance this equation. If total energy is zero, then you know this projectile has enough velocity to fly away from the escape the attraction of the star. The velocity is less than that, it will follow a parabolic trajectory back onto the surface of the star. So these gentlemen also were aware of the finiteness of the speed of light. Remember that Romer in 1676, using Jupiter's moons, had already computed the velocity of light up to an order of magnitude of 2, up to a factor of 2, I think. So they were on a very firm footing when they were postulating these kind of dark stars. Newton has also due to the formation of shadows and everything, posited this corpuscular or particle nature of light. So they really were on a solid footing when they said that light can be treated as a point particle, as a particle what moves with such a velocity v equal to c, finite velocity, and then you can plug it in this equation and you can ask what is the escape velocity for light. If speed of light be the escape velocity, the minimum radius of a star should be something like this. Actually, it's maximum. If the radius is any smaller, light will not be able to leave this planet or this star. It will shoot up a distance and then fall back down in a parabolic trajectory, which all of you kind of learn in middle school or high school. This critical radius is now modern day called the Schwarzschild radius. It's remarkable that this equation or this expression is correct even up to the factor of 2. It is correct with all numerical factors. It's an amazing fact that in a very approximate crude calculation, the answer exactly matches with the fully relativistic, full-blown computation. So, however, I would say these are not black holes. We will see what these black holes, what the word means. Words have very strong meanings. Dark stars, indeed, just dark stars in the sense that from distance, because light cannot escape, light goes up to a certain distance and comes back. They will appear dark from very far. However, if you're in the vicinity of the star, then you will be able to catch the light which is coming off the surface and then going back down. You can see that light. So near the star, these stars won't appear to be dark at all. So in the sense that these are not, although the formulas are deceptively similar, deceptively identical, be cautious that these are not what black holes actually were in the 20th century, the black holes we talk about. However, they are close cousins of that. Okay, so what is the full-blown general relativistic sort of solution for this black hole? First, people who are in the audience who are not familiar with general relativity, I have two equations, which are the equations of general relativity. Now, usually we only state just the first equation. The second equation I have kept for analogy with our comparison to facilitate sort of analogy with electrodynamics. When you have Maxwell's equations, if you write in the four-vector notation, Maxwell's equations turn into one equation, which is the inhomogeneous Maxwell equation, and the other is the homogeneous Maxwell equation. Similarly, in gravity, we have, instead of electric and magnetic field, or we have this curvature, which codes the gravitational interaction, or curvature stands for the gravitational force or gravitational curvature in the region. And T mu nu on the right hand side, instead of Maxwell's rho and J, you have this T mu nu, which is the stress energy momentum tensor. The components of the stress energy momentum tensor are your usual energy density, momentum density, as the name makes it obvious. These components are energy density, momentum density, so on and so forth, pressure, various kind of shearing stress, and so on. Just like in Maxwell equation, on the right hand side, you have charge density and current density. So this equation is not going to play a role. This homogeneous equation known as Bianchi identity is not going to play a role in whatever I'm going to say forward. Usually when we talk about Einstein field equation, we just need the first line. So you can ask what this R is. Just like electric magnetic fields are made up of potentials. What kind of potentials are there in R? R is actually made up of metric and its second derivatives. So R will have an expression in terms of G mu nu. G mu nu is the metric, and R is the curvature of that metric. Okay, the curvature of it usually is second order, made up of second order derivatives of the metric. Okay, so 1916, within months of Einstein writing this equation, Schwarzschild, who was fighting in the First World War, was able to write down a solution. Einstein himself never believed this equation could be solved because this is a highly complicated equation. As you can see, there are nonlinear terms. So this equation R is made up of a bunch of factors of G, so it's cubic in G. So this is a highly nonlinear equation, and Einstein was completely hopeless that anyone can ever find a solution to this. He never really tried it. It is ironic that within within a month or two of his writing down this equation, somebody found a solution to this equation. So maybe we should spend less time thinking how difficult the problem is, because the moral of the story is, if we start thinking about how complicated this equation is and how difficult it is, we psychologically build up a mountain which doesn't allow us to really climb that mountain and go to the other side. However, Schwarzschild was made a very simple guess, and he was not really thinking about how complicated this equation. He was trying to find out the simplest solution, and indeed he was successful in working out this equation. And this is the solution. I should tell you that when we mean what we mean by solving the Einstein equation is solving for this G. As I said, R is the curvature. Curvature can be determined from G. So when we say that we solve this equation, what I really mean is that we solve this G mu nu. The G mu nu is the metric components. They have been written in a way in which the metric components are these coefficients. You see this coordinate differential, dt squared, dr squared, and d theta and d phi squared. These metric coefficients G mu nu are these coefficients of this differential squared. Okay. So in case some of you are unaware, or if this slide appears a bit opaque to you, let me just tell you what these are. This G mu nu are basically the components of this dt squared, the coefficients. Okay, so we notice a strange phenomena here that when r is equal to this quantity, this critical radius, then this dt squared term goes away because there is no time direction in the metric. The metric becomes completely space-like, as if this metric becomes completely space-like because the time-like part drops off, it vanishes, and this radial part becomes infinitely large. Of course, this is an illusion because you can compute the length, which is integral of dr of this, that will be finite. It is not infinite. So we have one dimension being lost, the time dimension being lost. People regarded such a situation as very pathological. How can it be that a four-dimensional manifold or a four-dimensional space-time loses one dimension all of a sudden? Some random bad thing has happened, some pathology has happened. And they, for a while, they regarded this kind of clouded their thinking. Again, you shouldn't think too much about complicated things. That only makes your job difficult. They regarded it as this watch is singularity. This word singularity psychologically affects you because you really believe there's something wrong with this. However, it took a while before Lemaitre, the famous Belgian cosmologist, who figured out that there's no really singular, nothing really going on here. This is a completely nice place. There's nothing odd about this, nothing singular about this. Of course, there is something odd about this, which I'm going to talk about, but there's nothing special about this, which is so that you. However, there is a point which is r equal to 0, in which this component becomes infinite, right? And this goes to 0. So r equal to 0, you face a similar situation, except it's reversed. Time component becomes infinite, and this radial dr squared direction becomes 0. So is it like this RC? The answer is no, because you can compute the curvature scalar. This is sometimes known as the Kretschmann scalar, which is it's an invariant quantity. So you measure it in any frame, it will give you the same. So that's why we have taken r squared, because just r is not an invariant quantity. So if you measure this Kretschmann scalar, and if you compute the expression, it shows r 1 to the r over 6 in the denominator, which tells you that at r equal to 0, something really bad happens because this curvature blows up, it diverges. On the other hand, when r is equal to twice gnm over c squared, gn is Newton's constant in case somebody hasn't realized yet, then this remains finite and nothing really bad happens here, right? So in fact, this will become 1 over m to the fourth. So there's actually nothing blows up here. So r equal to twice gnm over c squared is a regular place, but r equal to 0 is a singular place. This is the bottom line. As I said, this is a regular place doesn't mean this is not a weird place. There are weird things going on here. So this was first demonstrated by Finkelstein when he constructed this coordinate system, which is known as the Finkelstein infalling frame, in which in general relativity you can do any change of coordinate systems because it's a general coordinate invariant. So instead of looking at this coordinate system, what Finkelstein figured out, this is problematic because it is not that there's nothing wrong with the geometry, but this coordinates t and r which we are using, there's something wrong with them. They're not a good choice of coordinate systems. People who have learned polar coordinate systems in the undergraduate classes will recognize what I'm trying to say. In polar coordinate systems, with cylindrical or spherical coordinate systems, r equal to 0 is kind of a singular place because you cannot define theta and phi on those along those points. And so it's a poor coordinate system in which you cannot specify the theta and phi. Instead of 3 variables, you have just 1 variable. So that description breaks down, and we have Cartesian coordinate system, which is better in that regard. At all points are more or less treated democratically. So choosing poor coordinate systems we are familiar with. So this is exactly what happens in the case of the Schwarzschild case. And what we have in Finkelstein's case, he wrote down a nice set of coordinate systems in which nothing really bad happens. But something weird happens. If you plot this dr over dv, r is the radial distance from the Schwarzschild, and v is the time, you can think of it, the infalling observer's time, or something like that, then this is proportional to this quantity which goes to 0 as r equals rc. So these are this equation which is for a null rate, because as I said, it's if you equate these two terms to 0, radial null rate. If you equate some of these to be 0, you get this equation. So it tells you that if this is 0, although I'm changing v, time is changing, my radius is not changing. dr over dv is 0, so I'm stuck at the same radius. So in fact, r equals to rc is an event horizon, which is a point of no return. Light rays can never go back. Now, if you're an infalling observer, what do we see? If you start to go out towards the horizon, but you will notice if you're inside the black hole, the horizon actually is moving away from you at the speed of light. So you'll never be able to catch up to the horizon, and you'll always be forever trapped inside. Okay. People who are claustrophobic, who are feeling bad about this, I'm sorry about it, but this is what is going to happen. You'll try to go towards the horizon, but it's going to move away from you at the speed of light, and you'll never be able to make it out of the horizon. So this marks the point of return, and Rindle aptly named it the event horizon, just like when after sunset the sun dips below the horizon, and we don't get sun's rays. Similarly, once an object goes below the event horizon, we are not able to receive any communication from it. No light rays come out. It's completely dark. So aptly, he named it the event horizon. Another crazy thing that happens is the amount of extreme time dilation which you suffer. Now, it so happens in gravity that your clocks depend on how strong the gravitational field is. Now, if you're near a star, if you're closer to the star, if you're deeper inside the gravitational well of the star, then your time actually slows up by this formula, which is given by this formula. This delta t is the proper time or a clock time at location r. And dt, delta t, this on right hand side, is the time at an observer at infinity, which is far outside the star. Now you can see there's a contraction factor, just like in special relativistic formulas, you have a Lorentz contraction factor. You have such a contraction factor, and in fact, at the critical radius, at the Schwarzschild radius, 1 minus 1, you get 0. So no time lapses at all. So this is in a place where extreme things can happen. So you will not experience any time lapse, or your friend who is waiting outside the black hole, way outside, for him many years would have passed. So the object never reversely. What happens is that when you have such extreme amount of time dilation, most of you know about gravitational Doppler effect. This time dilation, if you invert it, you'll get the change in the frequencies of the lights which are emitted from this location. Those lights will never appear crossing the horizon, or those lights will be extremely redshifted, and you will at some point you will stop getting the signal because they are taking infinite amount of time to climb out or come out. So from the outside, what will happen is that if you throw an object into a black hole, this object will never appear to cross the horizon because time is getting dilated. The object which is sending out signals to you, those signals are coming at very slow rate, and at some point that rate becomes exactly 0, so the object kind of freezes. But it's not exactly the object will freeze. Actually, this time dilation or this red shifting will cause all the visible light to go into the beyond. It'll be redshifted out of existence, so you'll just see a black patch, nothing else. No light will come out actually. The intensity also goes down because of the slowing down. So as you know, the brightness of something is given by the intensity. If the intensity goes to 0, then it appears completely black. So this time dilation phenomena is nicely demonstrated in this nice video which I have, in which what you have is two rockets which are surveying the hole on the same kind of radius. And at some point, one of them will blast his or her retro rockets and start falling in towards the horizon. So you can see this guy has frozen, and as a result, it cannot resist the pull of the gravity and is plummeting. And you can see the clocks will go out of sync. Now the clocks are not in sync. Initially, the clocks were in sync. As it goes down, it becomes redder as well because of the redshifting of light inside the gravitational well. And here, I don't know if you can guys make out, the clock is almost frozen, but this guy keeps continuing. As a result, you have a version of the twin paradox which you encounter in special relativity. In this case, now it can happen. You can hover around the event horizon of a black hole for, let's say, 10 minutes, and when you come out and back on Earth, maybe millions of years have passed on Earth. So you can use this extreme time dilation of black holes to build a future directed time machine. You can visit the future generations. You can skip maybe 10, 20 generations, and depending on the amount of time you spend near the event horizon, you will feel normal rate of time passage. But your friend on Earth, millions of years might have passed while you were just spending few seconds or few minutes here. So this kind of weird thing which have grown used to, and I hope in the future soon we will have experimental verification, because something which you can perform just outside the event horizon. It's not a experiment which you need to go fall into the horizon. So this kind of an experiment should be realized, and we should be able to see an experimental confirmation of this. Another crazy thing which happens is this tidal forces and spaghettification, this phenomenon which a lot of older researchers in black hole physics worried about. So what happens is, most of you know what tidal forces are from your Newtonian gravity classes. Tidal forces happen because an extended object, which is represented by these four green dots, suffers differential amount of gravitational force from the planet, from this planet here. So the legs will be pulled strongly apart because it's closer to the planet, while the head will be pulled apart less or a bit gently than the legs. And then the arms will also be pulled apart in the direction of the center. So as a result, there'll be a unbalanced force which is trying to squeeze this person. So this longitudinal stretching and this lateral squeezing, this kind of effect is very prominent when you have solar mass black holes. In fact, this is so large, the human body cannot withstand this kind of stretching and squeezing, and it will be ripped apart. It will be completely ripped apart. This is what exactly happens when accretion disks are formed. The nearby star, which is going around, it's slowly being ripped apart, its guts being spilled and sucked into by this black hole. But on the other hand, if we look at supermassive black holes, which a million or billion solar masses, 1 over m squared, the strength of the force means they're going to be very gentle. In fact, no more different from the Earth's gravitational field, what you feel on the surface of the Earth, that kind of tidal force. So you won't die there. But if you are near a stellar mass black hole, few for solar masses, then of course this will cause an enormous amount of tidal force, which you will not be able to withstand. And as I said, this is what is responsible for accretion disk. That is why supermassive black holes, very large black holes, you don't see accretion disks, except for quasars, but then they are very early universes. In general, for supermassive black holes, you don't see accretion disks. Of course, since this talk is about Penrose's contribution regarding black hole singularity, I cannot escape but putting in a small contribution which Penrose made about how exotic black holes are. And he actually outlined a process in which you can mine a black hole or get energy out of a black hole. Now, for this, you need something which is a rotating black hole or a Kerr solution. Now, a vast majority of solution black holes in the cosmos are actually rotating solutions. Spherical, static Schwarzschild black holes are, non-spinning black holes are actually quite rare. And I hope Roy Kerr, who invented or discovered this solution, will soon be given a Nobel Prize, because now we are actually seeing these, we are observing these very spinning black holes. So by rotating black holes, the solution covers a vast majority of objects we see in the cosmos. So hopefully Nobel Committee will take note of this and award him the prize before it's too late. The rotating black hole, let me show you a picture. This is what a rotating black hole looks like. Unlike the Schwarzschild black hole, you can see the horizon. They are not spherical. They have some kind of bulging. This is an effect of rotation, which you would normally expect. Just as in Earth, rotation causes the equatorial bulging, you have some kind of bulging here. Another phenomena you notice is two horizons, not one horizon. I have an outer horizon and an inner horizon. And the singularity is not at a single point, but it's spread out over a ring. So these details are unnecessary to what I'm going to talk about. But the only detail which is necessary about rotating black holes, which I want to talk about, is the presence of something which is known as ergosphere. Outside the horizon, something strange happens. For this, let me just briefly go back to the Schwarzschild solution here. Now, when r is less than this quantity, you can see that dt square coefficient will become positive, minus of a minus quantity. So this will be a positive quantity, and this will be a negative quantity. This is one way of saying that time will become space and space will become time. So for a rotating black hole, this happens before you cross the horizon. Long before that, long before you enter the outer horizon, time had become space. That is this ergo region. And Penrose devised a way in which you can extract energy out of this ergo region or ergosphere. I'm sorry about that. 1969. What he suggested is that since energy is conserved on a geodesic, what we can do is that you can follow a trajectory like this, a geodesic like this, and at some point in your geodesic, you dump something into the black hole. Now, because time has become space, energy of this dumped object energy is now not positive, semi-definite. Usually energy is positive. But whenever you have this ergosphere, energy, because this Time is now a space-like quantity. It's not a time, it's a space-like quantity. This energy can be negative. Now you can, I'm assuming that you can throw your object in a way that the energy is negative. And since the energy is conserved, the sum of two should be the energy with which you come outside. If the E1 is negative, then your E2, the energy which you emerge out of the zero region, should be greater than E0, your original energy. Now, this is very efficient, much more efficient than the solar nuclear reactions which we use for our powering our Earth. In fact, you can show that the sun, I think, loses only 0.6% of its mass in the form of nuclear energy. But if you're able to mine a black hole, if you're able to extract energy, you can go up to 29% of the rotational energy of the queer black hole that you can mine. So it's a much more efficient process. That is why in sci-fi novels you see advanced civilizations will try to colonize the queer black holes and then extract energy out of them forever. That will be much more efficient than the thermonuclear reactions happening in normal normal solar systems. Okay, so you might have gotten the impression that I've talked about things which are mathematical artifacts because these are not solutions which are not time dependent. The coefficients are all functions of space, so they are some kind of static or a stationary solution, non-time changing, not changing with time. So maybe these are my mathematical idealizations which don't have any truth to them, and in realistic process where everything is time dependent, they might not form. So the question is natural: do black holes form from realistic gravitational collapse of stellar matter after after the stellar matter runs out of its nuclear fuel? And the answer was the first, again, the shot in this direction was fired by Chandrasekhar, who said that indeed there is a chance that if the mass of this stellar matter is more than 1.4 solar mass, then electron degeneracy pressure cannot prevent collapse, and it might collapse indefinitely. There's no force which will be able to prevent this gravitational collapse into singularity. However, it turns out that there is something. Zwicky in 1934 posited the concept of a neutron star at the end of supernova explosions. He was fascinated with supernova, and neutron had been recently been detected by Rutherford's group, and so he proposed this concept of a neutron star in which neutron degeneracy balances gravity. And it turns out, indeed, even if you have more than 1.4 solar masses, you can balance a star if the star is made up completely of neutrons, which is a neutron star. And these actually, but Zwicky didn't really work out the math, unlike Chandrasekhar, who had an equation of state and everything, and he worked out. Tolman, Oppenheimer, and Volkov, they're in the same group as Caltech as Zwicky. They actually did the calculation, they wrote down the equation of state, some assumptions, and then they showed that if the star has mass more than 0.5 to 3, then you can neutron star more than this, 3 masses, solar masses, the neutron degeneracy won't be able to balance gravity, and the star would continue unabated its collapse. Oppenheimer, along with another student, also showed that collapse of a pressureless ball of dust does indeed lead to a black hole with a singularity in the center. However, all these were some kind of approximate theoretical pen and paper calculations. They were not really very hardcore calculations which will lead you to believe that these results. It so happened that, unfortunately, the World War II intervened, and then the Cold War intervened, and black hole research went into a deep freeze for about a long time, 15 years. And only after this super bomb or this nuclear bomb efforts were concluded, these programs were concluded in Soviet Union and United States, did scientists focus on this problem of black hole collapse once again. But now they were armed with much better tools, much superior numerical or computer simulations, in which they could simulate realistic collapse, including the effects of degeneracy, thermal pressure, high temperature, shock waves, which happen when matter tries to implode. These were all not taken into account in the earlier calculations, which are very primitive pen and paper calculations, nuclear forces, and then radiation. And sometimes there'll be, because of shock waves, there'll be mass ejection from the black hole, which will reduce the masses. So it was all these were done. The supercomputers which were used to studying nuclear bomb simulations were diverted to studying implosion, the reverse process of nuclear matter. And then it soon produced results, unambiguous results. in the United States, Colgate White and May, late 50s and early 1960s, did a lot of simulations in which they unambiguously concluded that the stars greater than twice of solar mass implosion beyond the critical radius. It will sink under the Schwarzschild radius. And because the Schwarzschild radius creates the event horizon, it will be forever cut off causally. No signals can reach us. So this kind of implosion is inevitable if the star is more than twice solar masses. And along the same time, but independently, the Soviet group led by Zeldovich, who was also involved in the bomb-making efforts of the nuclear bombs, his group also had simulations which confirmed independently the results of Colgate, White, and May, although they didn't know they were across the Iron Curtain, they didn't communicate with each other, but they independently arrived at almost the same conclusion. These gentlemen looked at supernova explosions, which lead to neutron stars, and Proddy-Retz ultimately looked at black hole formation when you have large mass black holes, almost similar, exactly the same results. So this put this idea on a firm basis that, okay, black holes are going to be there. If you have a large enough mass, there's nothing, no force is powerful enough to resist it. Stellar matter, and then if you allow it to sink below the critical radius, it will keep on getting crunched, and at the end, it will get crunched out of existence, to quote a phrase from John Wheeler at the whole center. Okay, so they will get crunched out of existence. Of course, people are not okay with this. Schwarzschild radius, they somehow swallowed a bitter pill, and they kind of agree that, okay, it seems like it'll go below the critical radius, but it will get crunched out of existence at the whole center. This was too much for them to swallow. And I'm sorry, there's some problem with my keyboard. It is always getting me, okay. So the doubts lingered on, and people were not happy with this conclusion. They were a usual thing when you're in a stage of denial. How can we say anything about the fate of imploding matter close to the center? You have high curvature and energies, and for this region, we have small regions, so quantum effects will become important. And we don't know anything about the laws of quantum gravity, so maybe these conclusions are not correct. Some people said that all this simulation was done for near-spherical collapse. Maybe their idealization and consequences of the spherical symmetry. If you don't have a spherical symmetry, and if maybe you're ignoring some important physical effects like rotation and other things, which would lead to the lack of formation of the singularity. There would be nothing would be crunched out of existence at the center of the whole. So even though these simulations were kind of decisive, people were not happy with it, including Einstein himself and many other people who actually believe that singularity cannot be a consequence of a theory which is as beautiful as general relativity. So before I talk about the singularity, I just want to review the mathematical properties of black hole, which were sort of found out in the so-called golden age of black hole research, or theoretical black hole research, from the mid-60s to the mid-70s. One important result of that was something which is known as the no-head theorem. Now, what is this no-head theorem? Which says that the final black hole doesn't remember anything about its history. It only remembers the mass it collapsed from. And it's always a perfectly spherical event horizon. It doesn't remember what material the original collapsing matter was made of, or which kind of a shape was it. It doesn't remember any of that. Once it sinks below the horizon immediately straightens out, or you can say horizon becomes shear. For example, you could have thought that this triangle, when it sinks below, collapses below its Schwarzschild radius, the horizon would have some kind of triangular edges or something out of them. It is true they do form, but once it's below the Schwarzschild radius, the triangle cannot communicate to the horizon that you should be a triangle. So the horizon sheds off those triangular protrusions in gravitational radiation, which is known as Price's theorem, that this gravitational radiation would cause all these protrusions of the horizon to go away and assume a perfectly spherical shape. This is sometimes known as quasi-normal balding, and this is because this is a no-hair theorem. So no-hair meaning there should not be any protrusion or any deformation from the spherical shape. Anything which is there will be shed off in the form of gravitational radiation. So these are the people who were responsible for this, not just analytical, but a lot of computer efforts were put into this. And then came the 4 laws of black hole mechanics, which again are a consequence of a lot of methods introduced by Penrose, this year's Nobel Prize winner. They had a set of bunch of 4 laws. Let me just write it. These are not important for today's talk, but let me just write it. There's the zeroth law, which mimics the zeroth law of thermodynamics. The quantity called surface gravity, which is, you can think of it as an analog of acceleration due to gravity, little g, on the surface of the event horizon. That little g is constant all over the horizon for stationary black holes. First law is that the energy, if you put some matter into it, the change in the energy of the hole or the mass of the hole is given by this amount. J is the spin, Q is the charge of the hole, and A is the area of the hole. And then the second law, dA dt, that is the area of a black hole, or if you have an isolated system of black holes, the sum total area always increases in any process, in any natural process. This is just a bit like your increasing of entropy principle, that in a spontaneously a system, isolated system, entropy always increases. And we also have some version of the third law, which says that surface gravity cannot be made to vanish, just like temperature cannot be taken to zero, absolute zero in finite number of operations. So these were like the peak of this golden age of black hole research. These results, these 3 or 4 results which I've written here. And after this, most of the work was diverted towards quantum understanding of the whole. Once we had that, we identified the black hole with a thermal object, which is a black body, which has a finite temperature and a finite entropy. The moment an object has finite temperature and finite entropy, it radiates. So black holes would radiate less like black bodies, which Hawking had proposed in 1975. And after that, most of the discussion about black holes would be in the quantum realm. So I'm not going to talk about them at all. So, but just for completeness, I kept this slide that there was a lot of work done in the mid 60s to mid 70s. Now let me come to the singularity, the unresolved question of the singularity. Whether the singularity is really there, or is it some result of some idealization or symmetry principle like spherical collapse? If we don't take spherical collapse, if we have rotation or something, do they go away? Sorry about that. So the first theorem regarding the singularity was by an Indian physicist known as Amal Rai Chaudhuri. Most of you have probably heard of him. In 1955, full 10 years before Penrose wrote down his singularity theorem, he was able to come up with a singularity theorem of his own. But his motivation was slightly different. He actually wanted to show that singularity is developed when you have spherical or this kind of an object, spherical kind of infall, and not for if you put rotation or acceleration, then singularities would not form. However, in the process, he developed some tools. For example, the Rai-Chaudhuri equation. Okay, sorry about that. So this paper contains a version of his primitive version of his equation, the equation named after him, Rai-Chaudhuri equation, which was to become the main instrument in all the future proofs of singularity theorem. So, although he didn't intend to, it was his tools which would be used to prove all the singularity theorem. So let me tell about his singularity theorem, which he had. For if this math is a bit opaque for most of you might not know general relativity. I will just explain what is going on. So what you have here is a time-like or null vector field u mu, which is a hypersurface orthogonal. So this u mu is normal to this constant f surfaces. Think about a surface and a normal sticking out of the surface. This u mu is going to be such parallel layers of such surface, and then u is orthogonal to that. Now you can write down an equation which looks like this, which is measuring this u mu d nu is kind of the directional derivative. You can think of it along this u direction. So how does this quantity change along as I go along this field u? Now this is sometimes this quantity del mu u mu. I'll have not time to explain, but this is sometimes known as the expansion theta. It's denoted by theta. And then this directional derivative is sometimes written in the lambda, where lambda is something which is taking you along this vector field u. Now this rate of change of this expansion of this theta, this expansion parameter, is given by a right-hand side, which is something like this. This is not the original equation. The original not the full equation. Full equation is some more terms which I've omitted. Only for this example is only for this paper where you have this kind of situation. So one thing to notice is that this quantity, this square quantity, the space-like thing, so it squares to a positive quantity. And because it has a negative sign in front of this quantity is completely negative. So the rate of change of this equation, the sign of this equation is entirely determined by this term, okay? By this second term. Now if for example theta is 0, if this quantity theta is negative, and this quantity is positive, because it has a negative sign in front of it, both quantities are now positive, so the rate of change of theta is now negative. And then what happens is that theta will attain infinite negative value for finite change in this lapse parameter, finite lapse in this parameter lambda, in the future. So in the future, this theta will become infinitely negative in finite amount of this parameter lambda along the u direction. Okay. So this situation, for those who were not able to, was a bit fast, this situation gives rise to a kind of singularity. If you consider this u mu to be motion of fluid, you can think of them as streamlines, the fluid streamlines. And if you have along these geodesics are, of course, most of you know what geodesics are. They're shorter distance lines. Now, if these u mu's describe the shorter distance line for a fluid moving along these geodesics, then this theta becoming infinite leads to the volume going to 0. Volume of a fluid, let's say fluid lump, a fluid sphere, that volume goes to 0. And as a result, the density of the fluid become infinite, unbounded. And this happens for the case of example which Raichaudhuri studied in this paper. And it does show that for reasonable energy condition, for reasonable conditions, the singularity will be inevitable. His logic was actually reverse of this. He wanted to show that, look, this only happens because I did not include terms which have rotations and acceleration. If I had included those terms, maybe this one singularity would not develop. So it's actually, he wanted to disprove the existence of singularities, and he wanted to show that singularities is a reason because you have spherical symmetry or some kind of idealization. However, in the process, he developed this equation which will serve as a great tool to prove the singularity theorem by Penrose and others. Okay, so what was wrong, not wrong, but what was the incomplete understanding that theta becoming infinite negative value, this is not a singularity actually. In general, it's a caustic. Okay, so caustic is just like you can imagine light rays converging at a point, a focus point. It's something like that. After that caustic, light rays can cross over smoothly and to start diverging. So just because you have a focal point doesn't mean there is something crazy going on, singular going on. So this is a focusing effect. However, this focusing effect for this condition will become very important when Penrose will pick it up and prove the existence of singularities. You will need one extra ingredient which Raichaudhuri missed, which was the closed trap surface, which I will come to later in a second. So this is a picture of Raichaudhuri. He was a legendary teacher as well. He sort of influenced huge generations of very well-known physicists. He taught an undergraduate in the Presidency College, and it's very rare that a self-trained person from India who was not a part of three major GR groups, either in Soviet Union under Zeldovich, or the American group under Wheeler, or the Cambridge group under Sciama. Someone who was a complete outsider made a very important contribution, which was to be the foundation of all forthcoming research about singularities. Okay, so it's a picture of him. And then I'm going to talk about Roger Penrose, to whom the prize belongs, for introduction of something which is known as global techniques. What do I mean by that? Now, Penrose was a complete outsider. He didn't have a training in physics. He was not a physicist by training. He was a mathematician. He was working on algebraic geometry. However, he was seduced into physics, space-time, and gravitation by listening to radio broadcast which the legendary Fred Hoyle used to make. So he was seduced into this, and then he used many of his techniques we learned from topology into physics, which were not known, and these kind of techniques kind of revolutionized the field. Until 1960s, before Penrose entered the picture, GI computations were done exclusively via local techniques. What do I mean by local techniques? Local techniques, I mean Einstein field equations were regarded as some kind of nonlinear second-order equation. So the whole game was to solve the second order partial differential equation with some sources, right? This was the whole game because it was very simple. It sounds simple. You're solving a bunch of nonlinear second order DEs. And then to get the global picture of space-time and matter, what you have to do is to solve locally around each event, presumably on a computer, and then patch together all the local results to get a full space-time picture of matter as well as space-time together. So this was the prevalent kind of way of working. So this is sometimes known as local analysis when we work with differential equations. Penrose, on the contrary, never cared about the differential equations. The reason is, since 1963, studies of black holes and singularity reveal powerful global laws and global properties of spacetime, which are not so clearly manifest when you treat Einstein equations as nonlinear equation. Going this route, these results are not so easily obtained. They are not transparently obtained. They're obscured by these. So you needed an alternative set of tools which were developed to analyze the global features of space-time directly without recourse to solving this Einstein equation. So you can find these in the textbooks now. It's a matter of textbooks. The textbook by Hawking and Ellis and the one by Wall 1984. These have these global techniques in which you can study directly Einstein the implications of global topology. So one of the techniques which Penrose introduced into GR was something about conformal infinity, the notion of conformal infinity, which I'm calling asymptotia. Now, most of you know from your undergraduate classes in electrodynamics, let's say, or electrostatics, that if you know the electric field or field at infinity from the 1 over r squared, the coefficient of the 1 over r squared fall off gives you the quantity of charge which is producing that field. Similarly, in general relativity, if you look at the form of the metric at infinity, then you can find out the mass and angular momentum, etc. All these are determined by looking at the asymptotic form of the metric. However, this is not so straightforward. Behavior at spatial infinity is not usually enough. For example, if you have a supernova kind of event going on in the inside space-time, then you should only, in order to measure the mass, you should always measure the mass after the radiation, which is carrying away the energy, passes the point at infinity you are standing. So one needs to know behavior of field at future null infinity. That is, taking large R is not enough. T cannot be arbitrary. You cannot be at arbitrary T. You have to have a T which is at a time which is future when the wave crosses R. Till the wave crosses R, if you measure the mass, it will give you the old mass, the pre-explosion mass. So you will not get the correct answer. So Penrose was able to realize that these are important, and he came up with a beautiful a technique which is known as conformal transformation, conformal compactification, in which you take the original space-time, do a conformal transformation is an angle-preserving transformation, which bring infinity to finite value of coordinates. So an example of this is flat space. I have suppressed the theta and phi direction in spherical polar type coordinates. Only the t and r directions are displayed. But you cannot see in this diagram is useless because you cannot see the infinity, minus infinity and plus infinity here. They're never going to be in a finite piece of paper. Instead, if you draw something which is known as a Penrose diagram, which is obtained by doing a conformal compactification. Conformal because you want to preserve cause-effect relations between events. So that's why conformality is important. And then compactification is what brings infinity to a finite point. So you can see now this diagram is bounded. All the infinities are actually at the boundaries of the diagram. Of course, the left boundary is just the origin, r equal to 0. It is not an infinity. But apart from this left boundary, everything else is infinity. For example, the top point, I plus, which I denote as I plus, is future time like infinity. This is where all massive particles end up in the future, infinite future. The bottom is I minus, little I minus. This is past time like infinity. This is where all time like geodesic or massive particles start out. And then this is I0, which is spatial infinity, which is actually R radius going to infinity. And then Penrose found out that there are two new types of infinities, which are future null infinity and past null infinity. They're denoted by the script I, sometimes called the scribe. Scribe plus is future null infinity. That is, light rays emitted end up here in the future. At infinite amount of affine time, they end up in this on this 45-degree line. and then they also emanate from this past non-infinity. Okay, so this was a it changed the game completely how we think about space-time, because you can see what's happening and you can see the causal relationship between various events from this. It'll become clear when I go to the next slide, which is actually a hand-drawn figure. I'm sorry I made this today morning. It's not very tidy, but the idea is that you can draw a Penrose diagram for Schwarzschild black holes as well. Now, Schwarzschild black hole, this is what it looks like. This is an idealization of a black hole, but let's look at this diagram, which is more realistic. The shaded region is some kind of matter which has collapsed to form the black hole. Now, if you compare with this is almost the same, except that something happened to the top part of the diagram. It got eaten up by the singularity. It is missing, right? Instead of the full diagram, what you have is some kind of truncation of the diagram. So this is what happens when you Schwarzschild black hole. What I will draw your attention to is the fact that I have drawn 2 points P and P prime. And what's so special about P and P prime, which we are going to need to know when we talk about singularity theorems, is that I have drawn two V's. You can see two V-like figures I have drawn here. Now, one of these, the right limb of this V is actually outgoing null ray, light ray, and this the left limb is an incoming light ray. Now, it so happens I've drawn some constant R lines. So here also I have drawn similar kind of a V-like thing. One is increasing R, and the one light ray is going in the direction of decreasing R. Now, inside the horizon, the game completely changes. You have this point P. Now, as I have shown that both these two surfaces are equal to 0. These are constant R surfaces, which are decreasing. So this is R equal to 2m, which is the horizon in both these diagrams. This dotted lines are the horizons. And then once you go inside the horizon, no matter which direction you emit light rays, you will always end up on a smaller radius. So light rays are converging. So whenever these both families of light rays will converge to a smaller size, that means this is very weird. We don't have intuition from this, but it does happen inside black holes. As I said, you're going to reach, no matter which direction you shoot light, you're always going to go further inside. You don't go outside. So whenever this thing happens, we call this surface P, this constant R surface P, which is a closed sphere, a closed trap surface or a trap surface. Now, this notion of trap surface, which was introduced by Penrose, which was the missing link in the previous singularity theorems. Without this concept of a trap surface, you cannot prove the singularity theorems. Once you have this trap surface, the proof of the singularity theorem become a bit more obvious, and you can immediately show whenever you have such converging light rays, something weird is definitely going to happen, and you're going to hit a singularity. So I'm going to skip this slide because this is we're already past time. So as I said before, we mentioned the proof. I mentioned the theorem. I will consider just what I mean by singularity. So I've been very glib about what a singularity is, very loose. But what I mean is that if there are some geodesics, I have a big paragraph here, but the bottom line is if you have some geodesics, they can be null, they can be space-like or time-like. If those geodesics abruptly end, they terminate at some point, then the termination point along with other adjacent termination points constitute a singularity. So this termination can happen due to either infinite curvature or some other region. So if it is impossible to extend space-time beyond that, which is why you cannot extend the geodesic, then you have a singularity. Okay. So this was a more rigorous version of a singularity than saying that space-time curvatures or densities become infinite, which was an important ingredient in the proof of the theorem. And then, as I mentioned, there is a trap surface which forms. Any closed two-dimensional surface for which the both set of light rays emitted converge, that is theta is less than 0. For example, in the Schwarzschild geometry, if you have any radius r less than the critical radius inside the horizon, then those spheres will be closed, will be trap surfaces. And of course, there's one more ingredient which is called a strong energy condition, which is given by, you've encountered this before in Raychaudhuri's equation. So if you can use Einstein equation to repackage this equation, it looks something like this. For every time-like vector field, this quantity is greater than or equal to 0. This is a reasonable energy condition. It's called, it just tells you that the pressure cannot be too negative or the density cannot be too negative so that the sum is always, less than zero. This is what it means. And of course, one more ingredient which goes into the theorem is the definition of a closed time-like curve. So causality, closed time-like curves are curves which are time-like, so that along that space is, you stay at the same location, but time is passing, something like that. If it's a closed curve, that means you can go into the future and meet yourself in the past. So causality is badly violated, right? Closed time-like curves are something which we don't allow for consistency. So these are the ingredients, and then now I am in a position to state the theorem, which is the original statement. I will talk about Penrose's original statement, and then I will talk about the more modern statement by a future, bit different statement by Hawking and Penrose later. If a spacetime described by a generic metric satisfying this energy condition for all, or this curvature condition for all null vectors, has a non-compact Cauchy surface. If you don't understand what the non-compact Cauchy surface is, don't worry. But has a trap surface. This is what I want to emphasize. This is the thing missing link between, I think, Raychaudhuri's and Penrose's formulation. Then spacetime is necessarily non-geodesic incomplete. So there are some geodesics which will end up incompletely. What do I mean by that? If I go back, here light rays will end up abruptly on the singularity. If you try to push this light ray through, where can it go? It meet the singularity and cannot go anywhere after that. So this is exactly what is happening. This is what Penrose needed to prove his theorem. Although the proof is complicated, I'm not going to talk about the proof at all. People can find the proof in Hawking and Others. Chapter 8 has a very nice way of elementary way of proving these. And then Penrose and Hawking wrote down a second singularity theorem, which in fact is a generalization of this. In a spacetime with generic metrics satisfying Einstein equation with sources which satisfy the strong energy condition. Remember, we mentioned what that is. If there exists a trap surface, then there must either be a closed time-like curve, which is bad, which we don't want, or a singularity. Now, the modern way of looking at it, a closed time-like curve is also a singular event. It's not something nice. All of a sudden, you have causality violation. So I would put this in the class of singularity as well. So in general, there's no way you can escape a singularity. Okay? So what is the moral of the story? The moral of the story is generic time-dependent situations in GR must develop singularities, or they will begin from singularities. For example, Big Bang. If you have a Big Bang, you don't have singularity in the future, but in the past you have. Now, GR doesn't apply to singularities because it's a singularity of description. It is something beyond which you cannot continue space-time, you cannot evolve geodesics. So that would mean GR is an incomplete theory, which is another conclusion from this. And it is true. However, one can take comfort in something which is known as cosmic censorship conjecture. Again, Penrose, the character who we are talking about over and over again in this talk, is that naked singularities cannot form in gravitational collapse from generic data. I think it got truncated, but let me just scroll down a bit. From generic matter collapse. Now, there's an emphasis on the word generic because you can have matter collapse. You can arrange for matter to collapse in a way, for example, very non-homogeneous spindle-shaped collapse in which naked singularities, which will develop, which are not closed by an horizon. So those singularities will be naked singularities that you'll be able to visible naked eye, and that would be a bigger violation of general relativity than, let's say, black hole singularities, which are cloaked by a horizon, because horizon prevents you from seeing the singularities. Your causal physics will not have, outside the horizon, your physics will be completely free from any influence of the singularity, and you can you can go ahead with normal life, without the effects of the singularity. However, naked singularities are even more blatant violation. That means you interact with it definitely, and whole formulation of GR is under suspect if you have naked singularities. Mind you, as I said, that there is some evidence for naked singularities in some simulations, although no one knows if it's a set of measure zero, whether they are too special, too exotic kind of collapses. So what is the conclusion and outlook? Let me finish with that. The conclusion is that of Penrose's work is that singularities are inevitable consequences of GR. The moment you have a closed trap from surface formation, that is a Schwarzschild kind of a horizon, inside you must have a singularity. There's no way around it. Nothing can prevent it. So this would mean that GR is incomplete. It is true that quantum gravity effects might ameliorate singularities. For example, in string theory, there are some cases in which singularities have been removed by string theoretic effects, especially for time-like singularities. However, for space-like singularities, string theory is still a long way to go in resolving what will happen, and we have to stay with this incompleteness. Penrose's methods, which he introduced, all these methods from global topology, actually revolutionized studies of GR and provided a global perspective. We came to know about new laws which didn't exist. For example, the black hole mechanics laws, some of them, the area theorem of Hawking, is a direct consequence of Penrose's methods. This area theorem of Hawking would not have, the second law would not be around if Penrose had not proposed his global tools. There is still the question of naked singularities, which is unresolved. There's still a question mark. As I said, some simulation data exists, including our very own from TIFR, Pankaj Joshi, who has shown that you can have some kind of very special collapse in which a naked singularities result. But as I said, there is still a question mark whether those special equations are too exotic. They form, in mathematically, we say, do they form a set of measure zero or not? Are they very generic or not? And the answer seems to be they're not very generic. And finally, I will say that the golden age of experimental black hole physics is upon us. So I believe next few decades we'll make many more fantastic confirmations. No matter how weird or strange they sound, those fantastic confirmations about black hole physics, including, let's say, Penrose process, might be confirmed. And we might make even new discoveries which will push further theoretical efforts. That's all. With that, I will end. That is all, more or less what I had to say. Thank you very much. Sorry I went aboard. Actually, I'm over time by 20 minutes or so. Okay, thank you very much.
Yeah, thank you very much,
please,
Dr.
if you have
Shubho.
questions from the audience, I'll be happy to take questions from the audience.
Yeah, thank you very much, Dr. Shubho. And right now, audience can ask us few questions because already we are running short of time. And so, if there are any questions from the audience,
Saket, are you saying something? I mean, you're mute.
Shubho, this is Priyatosh.
You can ask them to put it in the chat box, their questions, if they are interested.
Shubho?
yeah, if you can put your question in chat box, and then we will take few questions, actually 4-5 questions we can take. And after that, if any questions, you can ask through the email also.
Shubho, am I audible?
Yeah, please go ahead.
So there was one question from a student from ICER Kolkata. The student writes, I don't understand how the energy got negative in the ergosphere and how the extraction was possible.
Yeah, so I think that needs it's a very good question that needs a bit of an explanation, which I kind of rushed through. Of course, everything has to be done carefully. It has to do with the fact that in special relativity we have product of 4 vectors, and when you have a product of a 4 vector which is space-like, and when you have a product with a 4 vector which is time-like, for example, the stress, the energy momentum. Let me just go back to the slide. Yeah. So energy usually is given by this time-like vector k mu times dotted with the 4 vector p mu. Now this product, one is inside the horizon, one is space-like, and the other is time-like. So most of you know from special relativity, when you multiply 2 such vectors, the answer can be positive, negative, or 0. Right? One is space-like, one is time-like. It's indefinite. So, so in such a situation, what happens is that the energy, which is defined by the dot product of the killing vector with the momentum vector, that turns out negative. So that's how you can arrange for E1 to be negative.
Then the next question was how the extraction was possible.
The extraction was possible because once you push in negative energy from the hole, total energy, because the energy is conserved along a geodesic. If you have a killing vector, that means it's like a symmetry direction, so energy remains conserved. Now, so the total energy before this dumping and after this dumping should be the same. So that's why, and if this E1 is negative, so then E2 must be greater than E0. The energy with which I entered the ergo region must be less than what I leave the ergo region with.
I see. Okay, thank
Yeah,
you.
Dr. Shubho, actually, there is one question from Sambit Sarkar from IT Roorkee.
Yeah.
He's asking, can you briefly discuss how time-like singularity is resolved in string theory?
Yeah, it's very hard to do that briefly, but the idea is that time-like singularities, there are many. First of all, there are no single mechanism, there are different mechanisms. So I will give you one example is, for example, time-like singularities are time-like in the sense they are, they are extended in the direction of time. It's like, unlike space-like singularities, which are points at which space and time cease to exist, time-like singularities are located in space at a particular location in space, and you can avoid them. So in string theory, it turns out these time-like singularities are locations of d branes. Okay, so if you bring these d branes into the picture, then these time-like singularities go away, and it was some effect of an approximation. If you remove that approximation, when you bring in d branes, then these time-like singularities are resolved. There's something called resolved conifold, which I don't want to talk about. But if the person is interested, you can look up this resolved conifold story, and then you can follow what happened there. Another way is something which is known as the Gupser criterion or Gupser mechanism, in which time-like singularities can appear if you take, some kind of compactification of string theory and then take the compactification limit going to 0. In this limit, something crazy is expected to happen, and this time-like singularities appear. When you remove that approximation again, you get a smooth 10-dimensional geometry which has no time-like singularity. So there are different mechanisms which you can see string theory resolving time-like singularity.
Yeah, so Shubho, there is another question from Lakshman Mandal. Matter absorbs light because matter has band gap. Then how black absorbs light because black hole has no band gap?
I think the question is regarding that level spacing or some kind of band structure of a black hole or something. Am I correct, Sagar?
Yeah, Lakshman, can you? Yeah, black hole. He's telling black about the black hole.
Right.
Yeah, I think Shubho, the question is
Okay.
regarding black hole does have a band structure or not.
No, the answer is no. The answer is no. The reason is that the event horizon is the last surface beyond which, the matter which fell into the black hole, which is supposed to have a band structure, that has been crunched all the way to the singularity. It is empty. After you enter the horizon, there is nothing till you get to the singularity.
Subho, the question is not that one. So normally if you take the solid state materials like semiconductors, they absorb the light because there is a band gap. Now the question is that is there any band gap for the black hole since it is absorbing the light?
Oh, no. It is a different thing. You should think of it. It is disappearing down a hole. So a black hole is really, you can think of it. It is some kind of a trumpet, surface of a trumpet. And if you roll a marble down the trumpet will keep on rolling down. There is no end to that. It is entering a tunnel which is not ending. You're shining the light down a hole, literally in the sense of a hole. There is no absorption. There is nothing which is absorbing the hole. It is just that the light is completely disappearing down the hole. There is nothing absorbing.
Okay.
Thank you, Shubho. Actually, there are several other questions maybe there, but I request all the audience that okay, you can also approach to the Dr. Shubho anytime. You can explore the IIT Hyderabad and Department of Physics website. You can ask your queries, and then definitely he will be very happy to respond all those. And then I would like to thank you, Shubho, for his nice and informative talk on the Roger Penrose work and about the singularity concept. And then actually he's also working in the field of the singularity. And yeah, so I would like to thank you, Shubho, that okay, with very short notice, he was actually ready to present. the work. Actually, only I was just wondering that, okay, you mentioned about the A.K. Rai Chaudhary, the singularity equation. So, can you just maybe, because I'm not exactly in that field, that, okay, how much his contribution, people are actually, how much means, recognition people are giving to his singularity work, or
I
in the
think
in the Penrose idea, how much it was involved, that equation, Rai Chaudhary equation.
there is no way to singularity theorem without Raychaudhuri equation. That must be
Okay,
the
okay,
first
okay.
step of focusing. So I think if he was alive, he would have been awarded the prize as well, because, as I said, somebody who has given the first step and showed the direction how to do it.
Yeah, yeah, yeah. So that's why I asked actually.
Yeah.
So
Without Raychaudhuri, there would be no singularity theorem, period, because there would be no
yeah.
Raychaudhuri equation, and then Penrose would not have been able to follow up the proof. So
Okay, okay.
his contribution was indispensable. Without him, this would not be there.
And so many thank you messages from the audience actually in the chat box. And thank you, Shubho, very much. And then because your initials are like SR, so right now I can also tell you, I can also call you the Singularity Roy. So thank you very much,
No,
Shubho.
no, no. I am a regular person. Please don't call me singular.
Okay,
And,
So
okay, okay.
thanks a lot, Shubho.
yeah,
From my side, thank you very much. I just gave you 1 week time. I knew that but it was wonderful. This is the first talk I am hearing on singularity so far. And
yeah. This was not in the
so
domain of popular conscious, because only after the Nobel prizes, I think it has moved into public awareness. I think before that, public were not concerned. There was no need for concern.
true. Thanks a lot. Thank you very much. It was wonderful, wonderful
Uh,
talk.
thanks very much for giving me an
We
opportunity.
look forward to the next talk next week, same day, same time, right?
Yeah, yeah, sure, Dr. C. Please join the other talk on
Thanks
23rd
a
or
lot. Thank you very
27th by
much.
the
It was
Dr.
wonderful
Santanu.
talk.
He will talk about the rest two other people who shared the Nobel Prize. Okay, so please join and I will circulate all the information. Okay, so thank you very much.
Thank you.
Thank
Thank
you
you so once
very
again.
much for
Yeah,
the
thank
opportunity. Yeah, I'm very thankful to Professor Muti for giving me this opportunity.
No, it was wonderful. Thank you. Thank you very much.